In this lecture, we're going to introduce one of the most important ways to find antiderivatives and evaluate integrals with a method or technique known as substitution. All right, let's get started. As you continue through your journey learning about calculus through the calculus sequence, you'll encounter several ways to find antiderivatives and evaluate integrals. Of all of them, substitution, which we're going to learn about in this lecture, is arguably the most important for various reasons. So for that reason, we'll spend a lot of time on this lecture. We'll split it into two parts and take a look at a lot of examples to kind of thoroughly prepare you for what comes next in the calculus sequence. All right, let's take a look at a simple example here. It's an indefinite integral. This question is basically asking us to find an antiderivative for that function 3x squared times the square root of 1 plus x cubed. Now, at the end of your Calc 1 course, when you first learned about antiderivatives, you had a kind of a lengthy list of basic functions and their corresponding antiderivatives, which came by reversing all of your previous list of derivatives and differentiation rules. Well, if you take a look at this function, this doesn't seem to match any of those basic functions that have known antiderivatives. This one looks a little too complicated. Now, one problem-solving technique that is used a lot in mathematics is when you encounter a problem that you can't solve, is you try to relate it to things that you can solve. So here, we're going to try to relate this integral or antiderivative question to one that we do know how to solve. How we do that relating, we have to kind of somehow convert it, is we use a something to convert a complicated integral into one that is simpler. The something here that's going to do the conversion is what's called a substitution. So if we choose a substitution, we'll end up converting a complicated integral into a simpler integral. Now, what do we mean by simpler integral here? A simpler integral would be one of these functions that has a basic antiderivative, which you would, again, have learned to kind of at the kind of towards the end of your Calc 1 course. So at the top of that list, we have the basic power rule for antiderivatives. Add 1 to the exponent, divide by the new power. The power rule here doesn't apply when the power or exponent is -1. We have an antiderivative for e to the x, and then the antiderivatives of cosine of x and sine of x. And these are all basic functions with simple antiderivatives. That's what we mean in the basic idea here by a simpler integral. If we choose the correct substitution, we ideally get one of these simpler integrals here, one of these basic functions and their antiderivatives. That'll make more sense once we get to some examples. All right, now there's a number of ways that you could introduce substitution in a calculus course. One of my preferred ways to do this is to take as our starting place reversing known differentiation rules. So let's take a look at a statement. On the left, we have a statement written in the language using derivatives, and on the right, we have the same statement written or expressed using integrals as an indefinite integral. Both these statements on the left and right-hand side of the page have the same idea involved, that capital F is an antiderivative of little f. We can express that relationship using derivatives, or we can express that relationship using antiderivatives or indefinite integrals. All right, that's part of what we mean by reversing. We can reverse a statement expressed with derivatives. We can reverse it and express it using antiderivatives, indefinite integrals. Now let's think of our primary differentiation rules, the product, quotient, and chain rules. Of the three of those, one of them is arguably the most important. For a lot of conceptual reasons and how often you used it, I would argue that the chain rule is the most important differentiation rule. So it shouldn't be any surprise then that the chain rule, the most important differentiation rule, we're going to reverse it right now and get the most important integration rule. We're going to reverse the chain rule to get substitution, or the substitution rule. All right, so before we do that reversing, let's take a look at the statement of the chain rule as you would have had it kind of stated in your Calculus 1 course. Remember, the chain rule deals with ways to differentiate composite functions when you have one function inside another, f of g of x. Be careful, in the brackets there on that left side, that's not multiplication. That's not f times g of x, but rather f of g of x. G of x is plugged inside of the function f. All right, we can calculate a composite function's derivative using the chain rule as the derivative of the outer function with the inner plugged in. That's your f prime of g of x. And then we multiply by the derivative of the inner function, multiply by the derivative of g prime of x there. Now, the chain rule is all about inner functions. Well, for that reason, substitution is going to deal with inner functions a lot as well. Now, let's go back to the kind of top of this page. We're going to reverse this statement written in the language of derivatives. We're going to reverse it and get a statement now expressed as an integral, an indefinite integral. And basically all we do, instead of having a derivative on the left side of that statement, we can kind of reverse it and rewrite it now with an integral on the right side. And if we do that, rather anticlimactically, we get the substitution rule stated here. If we integrate f prime of g of x times g prime, that should come out to equal f of g of x plus a constant, since that's basically reversing the chain rule. Now, what we have here is an impractical version for substitution. We typically aren't going to, in practice and examples, use substitution written this way, but it is a conceptual starting place, which we'll be getting to in a minute or so. Now, let's just see where in this way of expressing this relationship, on the left side with that indefinite integral, where the inner function occurs. All right, and we have f prime of g of x. G of x is the inner function to f prime. And for that reason, since g of x is the inner function, we're going to choose it to be our substitution. You might have heard substitution referred to as u substitution or u sub. We choose a new variable u here as the inner function g of x. Now, what we're going to get to on the next page addresses why this substitution actually works. So let's keep going. Let's go ahead and see why that substitution works. Recall the basic idea that I want you to keep in mind for substitution. Substitution converts a complicated integral into a simpler integral. And let's see how that substitution, u equals g of x, does that here. All right, so I'm kind of just re-expressing what we had on the previous page, the reversal of the chain rule, now expressed in the language of integrals. And we were hinting at, we're going to choose u as g of x because g of x was the inner function. Now, how do we actually use this to convert to a simpler integral? Well, if we choose our u to properly convert, I'll say, some of the pieces in that integral, we have to calculate the differential du. If you continue on in higher level mathematics, you'll start to get a sense for what differentials really are. Right now, let's just think of differentials as a different way to express the relationship for derivatives. So we can say du is g prime of x times dx. So basically, du is the derivative of your substitution u, just with a differential dx attached. Now, with these two pieces, your substitution u equals g of x and its differential du, we can rewrite our original complicated integral entirely in terms of our new variable u. F prime of g of x, we can replace the inner part with u. We can rewrite that as f prime of u. And then from the differential, we can replace and rewrite g prime of x times dx. We can rewrite that as du. And what we have just done is express the original complicated x integral in terms of this much simpler integral in terms of the new variable u. Now, this certainly looks simpler since it's a much shorter expression, the integral of f prime of u du. It's also considerably conceptually simpler. We're integrating a derivative. Those processes should cancel out. So if we integrate little f prime, we should just get little f back. And since the variable here is u, we should get little f of u. All right, now how do we actually complete the question? Well, we're going to back substitute u as our substitution, and we get the answer that we expected from the chain rule, f of g of x plus a constant c. This is more or less what substitution is going to look like in practice. We choose a u, we calculate the differential du. If we chose correctly, then we should be able to convert to a much simpler integral in terms of u. Ideally, an integral involving a function that has a basic antiderivative. All right, we're going to take a look at our introductory example. But before we do that, I want to make some important remarks known and make them official. What substitution really does is it converts a complicated integral in the old variable x to a simpler integral in the new variable u. So keep that in mind. We're going to emphasize that. We convert an x integral into a simpler u integral. All right, that's kind of what substitution does, kind of what role it plays in questions at its foundation. But it doesn't tell you how to choose your substitution. So before we get to examples, here's 2 tips for how to choose your substitution. Since we were mentioning a few minutes ago that substitution comes from the chain rule, and the chain rule is all about inner functions, a primary way that we're going to choose our substitution u is by looking for inner functions. So we're going to look through our integral, and if we see a function inside another, that inner function might be a good choice for your u. Not always, but it's a good starting place. A second tip from what we see with converting using the differential du, whatever you choose your u as, you want to make sure that its derivative or differential du is a factor of the integral. Notice above why that makes sense. If we chose u as g of x, then its derivative, g prime, is a factor. G prime of x appears in that integral above. So that's something I want you to keep in mind as well. In order for it to be properly converted consistently, you need to have the derivative of u as a factor of your integral. We'll recall these as we go through some examples. Okay, at this point, we're ready for our introductory example that we brought up in the introduction. Let's go ahead and now apply substitution to evaluate this indefinite integral. All right, now, we were mentioning we want to take a look at inner functions, and we scan through and we see the square root of 1 plus x cubed. 1 plus x cubed is inside the square root. That's going to be a good first choice for u. So if we go with u as 1 plus x cubed, because 1 plus x cubed is the inner function to the square root expression, we can calculate the differential du as that derivative, 3x squared times dx. And if you take a look in the integral, what we're evaluating, 3x squared is a factor. So this choice seems to fit both tips that we gave for how to choose u. All right, now how do we actually use u in the differential to convert to a simpler integral? Well, let me rearrange some factors. We'll switch the order of multiplication. I'm going to move the 3x squared factor to multiply dx at the end. And now it might be a little bit more apparent how we use these pieces, u and du, to convert. We can rewrite the square root expression as the square root of u, replace the inner part with u. And using the differential, we can rewrite 3x squared dx as du. And if we rewrite that, we do get a much simpler looking integral in the new variable u. This is also conceptually simpler because square root of u, you can rewrite that as u to the 1/2, and now you can apply the basic power rule for antiderivatives. Add 1 to the exponent, 1 plus 1/2 gives you 3/2, divide by that new exponent, and we're basically done. Now, since we're starting with an indefinite integral in x, we want to give our antiderivative in that same variable x. So we convert back, we plug our substitution back in, u as 1 plus x cubed, and we get our antiderivative written or expressed in terms of x. And this is a good standard example kind of on how we're going to apply substitution and what the work looks like. All right, let's move on to a follow-up example. There's something common that happens in U substitution questions that I want to point out. Example 1 was evaluating the integral of 3x squared times that square root. Well, let's suppose for a follow-up example, we get rid of that factor of 3, and we're asked to evaluate the integral of x squared times that square root. What effect does taking off that factor of 3 have? All right, let's go ahead and kind of first start by choosing our substitution. Pretty much the inner function is the same, so we make the same choice for u. We calculate the same differential, and now we try to rearrange and rewrite everything in the x integral in terms of u. All right, well, the problem is our differential du has that factor of 3 in it. Our integral here doesn't. There's a few ways you can account for this. What I like to do is set up the idea of basically manipulating the differential. Think of the differential as you would like an algebraic equation, and we want to solve it for x squared dx. Well, we can solve for x squared dx by dividing by 3, and we can rewrite that statement as 1/3 du equals x squared dx. Now we can rewrite kind of all the pieces in our integral in terms of u. We can rewrite the square root as square root of u, and x squared dx, we can rewrite that as 1/3 du. So we get this, kind of integral down there, and we have a factor of 1/3 since we were missing that factor of 3 from the previous example. They're almost identical except for that. All right, so this is the way that I like to advocate to manipulate the differential, divide the 3 over to get a factor of 1/3, and then all the pieces can fit together. There are equivalent ways, but this idea of manipulating the differential will set us up for something that comes later in some following examples. All right, at this point, we're basically done. This is pretty much the same problem, just with a factor of 1/3. So you should be able to kind of finish that no problem. All right, let's take a look at kind of a follow-up, example 2. At this point, pause the video and give an attempt at these 2 examples. We'll check in a few minutes. All right, welcome back. So if we go through part A, there's really not a lot of choice for your u here. So we're going to go with taking a look at the inner function, what's inside the exponential. So we'll choose u as 3x plus 1. We calculate the differential, du, as 3 dx. And we notice when trying to rewrite all the different quantities in our integral, we don't have a factor of 3. No problem. We can solve for dx, divide the 3 over, to express that as 1/3 du equals dx. And now you can rewrite your integral as the integral of 1/3 e to the u du. At that point, we know the antiderivative for the exponential function itself. So we get as our antiderivative 1/3 e to the u plus c, and we back substitute our u in terms of x. So we get our antiderivative here, 1/3 times e to the 3x plus 1 plus your constant c. All right, this one was also a straightforward substitution. Let's take a look at part B, which is similar. Again, there's not a lot of choice for your substitution u, so we can go with the inner function u as 2x. The differential would be 2 dx. We don't have a factor of 2 in our integral, so we can divide it over and solve for dx and rewrite that differential as 1/2 du equals dx. Now you can replace and rewrite it as the integral of 1/2 cosine of u du. Again, the 1/2 is coming from the manipulated differential, dividing the 2 over. And at that point, we know an antiderivative for cosine, which would be sine. So the variable here is u. We get as our antiderivative 1/2 sine of u plus a constant, and we back substitute u as 2x. All right, now these weren't intended to be complicated or difficult. They're just going to lead us to a shortcut, which we're going to kind of summarize momentarily. Both these examples made a substitution that was the inner function. What's special about these two examples is the inner functions were similar. 3x plus 1 and 2x, those are both linear expressions. They fit the form ax plus b, or what you might call, like the equation of a line, mx plus b, just different symbols. All right, now take a look at your answers that you found. In the first substitution, u equals 3x plus 1. The value for a is 3. We get a 1/3 in our antiderivative. In part B, we have the substitution u equals 2x. The value of little a is 2, but in your antiderivative, you have a factor of 1/2. Well, let's go ahead and summarize this. This is a shortcut that we're going to be using throughout the course, and what continues kind of through the calculus sequence when you have a basic function with a linear expression inside. So integrals of the form a function of ax plus b, where a and b are constants. All right, so let's keep in mind the two examples, example 2a and 2b. We just put up on the screen here. And we have the original problem and the antiderivatives, the answers. All right, do we notice a pattern? Well, let's kind of go into detail. Let's say for the general expression, the function f of ax plus b, think of what the inner function is, ax plus b. Let's try that as our u. With that u, we can calculate the differential du, which would just be a. That's the derivative of ax. B, a constant, differentiates to 0. And we want to kind of rewrite and solve for dx to properly convert this integral from x to u. So we can divide the factor of a over to get 1/a. That's going to be the kind of main theme of this shortcut. And if you properly convert your integral from x to u, you get the integral of 1/a times f of u du. Now what's important here is to see where the 1/a factor comes from, basically by your substitution and then manipulating the differential. Ideally, at the end here, the integral of f of u du, ideally that's a basic function that has a known antiderivative. All right, now let's take a look at some examples where we can make use of this shortcut. We're going to informally call this the 1/a shortcut. And pretty much, as long as we have a function that has a basic antiderivative, this kind of cuts out some of the work in doing a substitution. So let's say for the first example down there, we take a look at the integral of e to the negative 2x. Now here, we're going to identify the inner part as being of the form ax plus b. And for this inner expression, little a would be negative 2. Now, you can go through and carry out in detail a u substitution. Try here u as negative 2x. But we're going to make use of this shortcut. We have the factor of a identified. A is negative 2. And we know a basic antiderivative for the exponential function. What this shortcut says is our antiderivative has a factor of 1 over a. That's the negative 1 over 2 factor. And then times the basic antiderivative. And we plug the linear expression back in. All right, as a second example, just to see how it's used, this is intended to make some problems later go a little quicker. Let's say we have the integral of 1 divided by 3x plus 2. Now the linear expression is in the denominator of the form 3x plus 2, little a would be 3. Now, if you were to do a u substitution in detail, you'd end up converting this integral to 1 over u. Do you know an antiderivative for 1 over a variable? You should. 1 over x has an antiderivative of natural log of x. So we have a basic antiderivative here for 1 over u, natural log of u, but since little a was 3, our antiderivative has a factor of 1 over a, 1 over 3. And we basically just multiply. We get our answer, hopefully quickly, as 1/3, that's your 1 over a factor, times that function's basic antiderivative, natural log, and then of the linear expression, 3x plus 2. Now, if this sounds confusing, maybe go through a few examples carrying out the substitution in detail, just so you get a sense for where the 1 over a factor comes from. And then through a few examples with some practice, you'll probably start to incorporate this, especially as you continue on through learning other methods for finding antiderivatives.